So basically binary tree is a non-linear data structure. Means the elements are arranged in hierarchical manner. So the elements are not in 1, 2, 3. The elements are present like this. So this is the hierarchical manner. The elements of these are called childrens and these are called node or root. So like this way hierarchically manner the elements are arranged. So it is the binary tree. If we apply some conditions to the binary tree, it becomes binary search tree. Why we use binary search trees instead of binary tree? Because binary tree has high complexity and there are many drawbacks. To overcome that drawbacks, we use binary search trees. Binary search trees is a type of binary tree, but we apply some conditions. In binary search tree, first condition is the root is present at middle and the values less than the root are present at left and greater than the root are present at right. So this is the mainly condition for the binary search tree. So the by so making binary tree as a binary search tree, there are many uses like for searching, deleting and insertion. So there are many benefits of using binary search tree instead of binary tree. For searching, deletion, insertion, the complexity in the binary tree is very high. To decrease the complexity and increase the efficiency, we use binary search tree. So using a binary search tree is a good practice in coding.
Insertion in binary search tree. A new key is always inserted at the leaf by maintaining the property of binary search tree. If key value is less than root value, move to the left subtree. Otherwise, if key value is greater than root value, move to the right subtree. Let us discuss an example. Here we take binary search tree. We have to insert x is equals to 40. It is the key value. Now check 40 with 100. 40 is less than 100. So we have to move left subtree and then compare x with root value. 40 is less than 100. So we have to move left subtree and then compare with 20. 40 is greater than 20. So we have to move right subtree and then compare with 30. Here 40 is greater than 30. So we have to insert 40 as right child of 30. Now let us discuss program. Let's discuss program using recursion in Python. About insertion, we have to compare key with root. If root is none, directly we have to insert key. Else we check root value less than key. We have to insert key at the right subtree. Else we have to check root value is greater than key. We have to insert key value at the left subtree and return the root. Insertion of binary search tree. First consider 50. Here 50 we can insert directly. And then take 30. Here 30 is less than 50. So we have to insert as left subtree of 50. And we consider 20. Here 20 is less than 50 and then compare with 30. 20 is less than 30. So we have to insert 20 as left subtree of 30 and then consider 40. Here 40 is less than 50. So we have to move left subtree from 50 and then check 40 is less than 30 or greater than 30. Here 40 is greater than 30. So we have to insert 40 as right subtree of 30. And then we have to consider 70. Here 70 is greater than 50. So we have to move right subtree and insert directly. Consider 60. Here 60 is greater than 50 and then compare with 70. Here 70 is greater than 60. So 60 we have to insert as left child of 70. And then consider 80. Here 80 is greater than 50. So we have to move right subtree and then check 80 is greater than 70. So insert 80 as right child of 70. Thank you. Deletion in binary search tree. The task is to delete a node in binary search tree. We have three scenarios. The first one is delete a leaf node in binary search tree. Here example is we have to consider 10. Here 10 is leaf node. So we have to delete directly. After deletion we get this case 2. Delete a node with single child in binary search tree. Here we have to delete 70 because 70 contains single child. We have to replace 70 with 80. After we get 50, 30, 80, 20, 40, 7.
Predecessor of 19 will be 17. The third condition to find predecessor of a given node is it doesn't have any left subtree and it is the right child of its parent. For example, consider 76. 76 doesn't have any left subtree and it is the right child of 72. In this case, the predecessor of 76 will be its parent node. So the predecessor of 76 will be.
This is the program for deletion in binary search tree. Here x is considered as node to be deleted. We check root is none. We have to return root directly. Otherwise we have to check root key is greater than x. We have to move left subtree and delete the element. Case 3. Delete a node with both children in binary search tree. Here we have to consider to find inorder successor else inorder predecessor. Example for delete a node with both children in binary search tree. Here we have to delete 50. So we have to check inorder predecessor or inorder successor. Here I consider 60 as inorder successor. So we replace 50 with 60. We get 60, 30, 20, 40, 70, 50, 80. Here the 50 we consider to delete. So we can delete directly because here the 50 is child of 70. After deletion we get 60, 30, 20, 40, 70, 80. Else if key less than x, we have to check right subtree and delete node present at the right child. Else, above conditions are not satisfied, we have to check. This is only for right subtree. If left subtree is none, we have to delete element present at the right subtree and return the deleted node. This is only for left subtree, so we have to check. If right subtree is none, we have to move to the left subtree and delete node present at the left subtree.
So today I am going to explain you about the height of a binary tree. So basically the definition of height of the binary tree is the number of edges in the longest path from the root to the leaf node. So here we can see the example. Here the root node is 50 and the leaf nodes are 9, 14, 23, 67 and 76. So leaf nodes are basically defined as the nodes without children. Without any children, it does not have at least one children also, so we can call them as a leaf node. So here in this example there are 3 edges from the root node to the leaf node, so the max height is 3. The height of the tree is equal to height of the root. Height of leaf node is 0, so leaf node does not contain any children, so the height is 0. Height of a node is the number of edges in the longest path from the node to the leaf node. So here if we consider 17 as a node, so this height is 2. From 17 to leaf node 9 there are two edges, so the maximum height is 2. So when we write the code, we can write code as recursively. So we find the height of a binary tree, and first we have to find the height of the left subtree and the height of the right subtree, and then max of height of left subtree and right subtree plus 1 is the height of the binary tree. We add plus 1 at last because we have to include that the root node. Here is the code of the height of the binary tree in Python. So here we basically use the concept of recursion to calculate the height of the binary tree. First we check that the root is none. If the root is none, there is no height. So we return minus 1. If we return 0 here we are adding 1. So the height of the root will become 1. So we use here minus 1. Then 1 minus 1, 0. So the height of the root will become 0. So after checking if root is present or not, we come to check that the height of the left subtree. So the height of the left subtree, we recursively call the function, and here we pass root left to traverse to the left instead of passing root. After calculating the height of the left, we come to the right and we calculate the height of root right. Here it goes to this function, and here it passes root right, and if root right is none, it returns minus 1, else it returns the height. So after checking the left and the right height, we return the 1 plus max of left height come. Here suppose this is the tree, and here we have the left height is 1 and the right height is 1, and the max of 1 and 1 is 1. So 1 plus max of 1 comma 1. Here it takes 1 plus 1. So 2. Height is 2. So like this we calculate the height of the binary tree. So I am going to explain about the level of any node in a tree. So the level is basically defined as the number of nodes from the root to the leaf node. Here 3 is the root node and 1 is the leaf node because it does not have any children. So level basically starts from 1. The level of the first root node is 1. So in other words, we can say level as 1 plus depth. So take the example of 1. So to find the depth of the 1, we move backwards. So the depth of 1 is number of edges from back side. So here we have 2 edges from 1 to 3. So edges from leaf node to the root node. So here we have 2 edges. So the depth is 2. And the level of 1 is 3 because level equals to 1 plus depth. So here is the sample code to find the level of any node in a tree. especially binary search trees. So here we start from the root as level 1 because the level of the root node is 1. If the key matches the root data, we return level and recursively call left and right subtrees with the level as level plus 1. So here basically we use the concept of recursion to write the code. So here we define the function and pass it parameters root, key and the level equals to 1. Here we pass a level is equal to 1 because the level of the root node is 1. So if there is no children for a root node, then the level is 1. So here key is the element that we want to find the level. If first here we use looping statements. If root is none, return 0, and if there is no root in the tree, so tree does not exist and we return 0. There is no level for it. If not root is none, we come here and the root dot data equals to, and if another condition, if root exists and root dot data is equal to key, we return level. And after if key less than root dot data, and we go to left subtree because as per the conditions of the binary search tree, the left side are less and the right side are the higher elements. We go to right and here we check level of root right key, and we here if the element is present we increase the level. Likewise in right subtree also. So here we take the example of 3, 2, 1, 5, 4, 7. So this is the binary search tree. If you want to know the level of the tree, 2. So here key is the 2. And here we check condition. If root is none, so root is not none, and this condition is false and comes and it cursor comes here and root dot data is equal 3 equals to 2, condition is false and it comes to next. If key less than root dot data, 2 less than 3, condition is false, it comes to the left subtree and finds the level and increments the level here 1. So here increments level, so 1 plus 1, here the level becomes 2 and returns 2. So this is the sample code. Thank you.
About leaf node. In a binary search tree, a leaf node is a node that does not have any children, that is, it has no left or right child nodes. Leaf nodes are always located at the bottom of the tree. Let us discuss an example to know in detail about leaf node. Consider a tree. In this tree, 15 is a root node, 10 and 20 are the child nodes of 15, 18, 12 are the child nodes of 10, 17 and 25 are the child nodes of 20. Now, in this example, we will find which are the leaf nodes and which are not. 15 is not a leaf node because it has child nodes 10 and 20. 10 is not a leaf node because it has child nodes 18 and 12. 20 is also not a leaf node because it contains child nodes 17 and 25. 8 is a leaf node because it doesn't have any left child or right child. And 12 is also a leaf node because it doesn't have any left child and right child. 17 is also a leaf node because it doesn't have any left child and right child. In the same way, 25 is also a leaf node. Here is a function in Python to check whether the node is a leaf node or not. For example, consider 8. In node dot left means it will go to its left subtree. Whether here there are no any child to its left in its left subtree, so it will return null. But the condition is true. And in node dot right, it will go its right subtree and check whether there are any child nodes or not. Here there are no any child nodes for 8, so hence the condition is true, and this condition is true for in case of 8, so it will return true. For example, consider 10. Here in this condition node dot left, it will go its left subtree. Here the 10 has a left subtree of 8, hence the condition is false, and it will execute from this condition and it will goes to else condition and it will returns false. We are going to discuss about finding the min and max element of any node in a tree, that is inorder predecessor and inorder successor of any node in tree. First, suppose before going into inorder predecessor and inorder successor, first of all discuss about inorder. Inorder. Inorder is always in a sorted order, because in inorder it will traverse, first of all it will traverse the leftmost subtree, then it will goes to the root node, and after the root node it will goes to the right subtree. Here example, here 15 is a root node and it will goes to the left subtree. The left subtree of 15 is 10, and here 10 also has a left subtree, and the left subtree of 10 is 8. Here 8 is a leaf node because it doesn't have any left subtree and right subtree. Therefore, the inorder will start with 8. Then it will goes to the root node. The root node of 8 is 10. Then it will comes to the right subtree. The right subtree of 10 is 12, and 12 is a leaf node because it doesn't have any right subtree and left subtree. In the same way, it will traverse the overall tree. Therefore, the inorder of the given tree is 15, 17, 20 and 25. Now we are going to discuss about inorder predecessor and inorder successor. Successor. The successor of a node is a node with the smallest key greater than the given node. Means if we have an inorder, in that inorder the successor is, for example, if you want to find the successor of 15, successor will be the next element of the node we have to find. 17 will be the successor of the 15. Predecessor. The predecessor of a node is the node with the greatest key smaller than the given node. For 15, 12 will be the predecessor. Means in a given inorder, we see that 10, 8, 10 and 12. In the 12 is the greatest, and it is the smaller than the 15. So 12 will be the predecessor. There is no inorder, and we have to find the successor of any one node in a given binary search tree. There are three conditions. In that, the first condition is the node has a right subtree. Means if, for example, let us go with 17. If you want to find the successor of 17, here the 17 has a right subtree which is 23, and the 23 has a child of 19. In this case, the successor of 17 will be 19, because if it has a right subtree, then the successor will be the leftmost node of the right subtree. Means here it will be the right subtree and the leftmost node is 19. So hence the successor of 17 will be 19. For example, in this case, consider here 19 has a child of 18. If you want to find the successor of 17, in this case, the successor of 17 will be 18, because the leftmost child will be 18. Hence, the successor of 17 will be 18. Condition to find the successor of a node is the node doesn't have a right subtree and it is the right child of its parent. Means if we want to find the successor of 23, in this case 23 doesn't have any right subtree, it only have left subtree, and it is the right child of 17. In this case, if we want to find the successor, then to find the successor we have to traverse upwards. We have to traverse upwards and upwards the tree until you find a node that is left child of its parent. Here the 23. Next we have to traverse up 17, and here we find that 17 is the leftmost child of 15. Then the successor of 23 will be the parent of this 17. The parent of 17 is 50. So the successor of 23 will be 15. Condition to find successor of a node is node doesn't have any right subtree and it is the left child of its parent. For example, consider 19. Here 19 doesn't have any right subtree and it is the left child of 23. In this case, the successor will be the parent node. Means 19, the successor of 19 will be 23 because it doesn't have any right subtree and it is the left child of its left child of 23. In the same way as successor, predecessor also has three conditions to find the predecessor of a given node. Predecessor is the opposite to the successor. First of all, if you want to find a predecessor of any particular node, we have to check whether it has left subtree or not. If it has a left subtree, then the predecessor will be the rightmost leaf of the left subtree. Means let us go with an example to understand in detail. For example, if you want to find the predecessor of 17, consider a tree. In this tree 17, the 17 has a left subtree of 12, 9 and 14. Find the predecessor of a given node, we have to check whether it has a left subtree or not. If it doesn't have a left subtree and it is the left child of its parent, in this case we have to traverse up the tree until you find a node that is right child of its parent. In this case, the parent will be the predecessor of the given node. For example, if you want to find the predecessor of 19, here take 19. 19 doesn't contain any left subtree. In this case, we have to traverse up. We have to traverse up until you find a node that is right chain. Okay.
To explain the code for predecessor and successor. Predecessor mainly found in the tree's right side and successor mainly found in the tree's left side. So this is the code for the predecessor and successor. First we go through the predecessor. Predecessor is available in right subtree and it is available at the last if we take the root node as a element. So we send the nodes right and current equals to node right. Take a temporary variable and store node right. And the least element in the right side is available only in the left side, and we check if current left is not none. If it is none, it becomes the current and it will be the least node, and we return that. If not none, we traverse through the tree until we found the last element. So if we found the last element, we return that one too, so it becomes predecessor. Likewise, successor. Successor is mainly found in root left. So left side, and we send node left as a parameter and we store it in a temporary current variable. And while current left, and the highest element in the left subtree is always found at the right side, so we go through the right side. While if current right is not none, and we go through the tree and we traverse to the tree, and if the condition fails, current right becomes none, and we return the current because it is the last most subtree, and we return that one.